Action potential. Phases of action potential. Action potential pass into the following phases. From the start, this is the resting membrane potential. Upon stimulation, there is stimulus artifact, followed by latent period, number 2, then gradual depolarization, number 3, then rapid depolarization till reaching the overshot, where reversal of polarity occurs. The nerve fiber becomes completely depolarized to reach the level of positive 35 millivolt. Then repolarization starts by rapid repolarization, number 5. Initial rapid repolarization. Then repolarization becomes slow to form negative after potential. Then there is undershot of repolarization forming positive after potential, and finally it will reach the resting level. This undershot will return to the resting state to become minus 90 millivolt. This action potential which we describe in the nerve fiber, large sized nerve fiber. So again, action potential is formed from, upon stimulation there is stimulus artifact, there is latent period, initial slow depolarization, then rapid depolarization to reach the overshot and the reversal of polarity, then rapid repolarization and slow repolarization formed from negative after potential and positive after potential. So the phases again, number 1, stimulus artifact, this one, site of application of stimulus, then latent period from application of stimulus till start of the action potential, then initial slow depolarization from minus 90 to minus 65 millivolt, then rapid depolarization. Upon minus 65, it is the firing level upon which all sodium channels will open to give sudden fire, sudden ascent of depolarization. Then rapid initial repolarization here, and negative after potential, and then positive after potential, and finally return to the resting state. This is description of the phases of the action potential. What about the ionic basis of action potential here, or genesis of action potential here? At the site of stimulus artifact, as we see before this part, resting membrane potential is stable, minus 90 millivolt. Upon stimulation, there is irregularity in this resting membrane potential due to leakage of some current from the stimulus, and it indicates the site of application of stimulus, so it is called stimulus artifact. Between this point and the start of depolarization, it is the latent period. Sodium channel start to open. Activation gates of sodium channel start to open. So sodium influx start to occur, and it is a positive feedback mechanism. Once sodium channel open, it helps others to open, till reaching the firing level by this positive feedback mechanism, where almost all sodium channels open, causing sudden ascent to reach the overshot due to sodium influx. So the gradual increase in depolarization is due to opening of sodium channels in a positive feedback fashion and sodium influx. Then rapid depolarization is caused by sodium influx. This overshot unreached stopped to this point due to what? Due to two causes: closure of sodium channel and sodium influx stop, and the potassium channel start open and the potassium influx start to occur. Initial rapid repolarization occurs due to these two causes: closure of sodium channel and opening of potassium channel. At that point, the potential difference, ionic concentrations between outside and inside the nerve regarding potassium is high. So rapid potassium efflux occurs causing initial rapid repolarization. Upon time, this concentration gradient decrease, causing slow repolarization. And as the potassium channels close slowly and delayed closure, there is undershot reaching to minus 92 millivolt. Then, to return resting state, sodium potassium pump occurs, and they are responsible to return this undershot to the resting condition. So to summarize again, initial rapid depolarization, initial slow depolarization is caused by sodium influx in a positive feedback fashion due to opening of sodium channel in a positive feedback fashion. Then sudden ascent due to opening of all sodium channels and sodium influx. Initial rapid repolarization due to potassium efflux, and the big difference in ionic concentration in potassium between extra and intracellular fluids. Then slow depolarization in the form of negative after potential and the positive after potential. Negative after potential due to decrease this concentration gradient and the continuous potassium efflux. This undershot in positive after potential due to delayed closure of potassium channel and the continuous potassium efflux. Upon reaching minus 92 millivolt, sodium potassium pump acts to return the nerve membrane to the resting condition, to return to minus 90 millivolt.